Okay, so in this video I'm going to sketch the curve of y equals x cubed divided by 1 plus x squared, all this by hand, and then I'll compare the solution with what I would get using a graphing software. Now, before we actually sketch the curve, I've listed up here the main features of any curve. We've got to have intercepts, we've got to have asymptotes, turning points, and sometimes you may need to know the nature of the curve, where the curve lies and where the curve does not lie. Alright, so let's begin with the first one, the intercepts. So we'll go intercepts. As you understand, we need to have x-intercepts and y-intercept. So let's begin with the x-intercept. So the x-intercept. At the x-intercept, it's important to know that the y value is equal to 0. So if I have the y value as 0, if I substitute 0 in this equation, 0 equals x cubed divided by 1 plus x squared. This implies that x is also 0. So the y at the x-intercept is 0, 0. Let's go ahead and find the other intercept, which is the y-intercept. So the y-intercept, at the y-intercept, obviously x equals to 0. So y is going to be 0 cubed divided by 1 plus 0 squared, which implies that y is 0. So the intercept here is also 0, 0. Okay, so the x and y intercepts are both 0, 0. Let's go on to the asymptotes. We're now looking for the asymptotes. I'll begin with the horizontal asymptotes. Let's begin with the vertical. I think that's a little bit easier, so to say. So let's work on the vertical asymptotes. For us to get the vertical asymptotes, we just have to equate the denominator to 0. So for the vertical asymptotes, 1 plus x squared equals to 0. And as you can see, this equation here does not have any real roots. Oops. Okay, so this equation here doesn't have real roots. So I just say no real roots. No real roots. So we conclude that there are no vertical asymptotes for this graph. No vertical asymptotes. Okay, let's now work on the horizontal asymptotes. Sometimes we call that the slanting asymptotes. Alright, so the horizontal or slanting asymptotes. Now, if you look at this curve, it's actually an improper fraction because the power of the numerator is actually power 3 and the highest power of the denominator is power 2. That's x squared. So this is actually an improper fraction, and it's necessary for us to use synthetic division before we actually go ahead to find the slanting asymptote. So let's divide this x to power 3 divided by x squared plus 1. So x to power 3 divided by x to power 2. We've got x here, so I multiply x by this. I have x squared plus x. And if I subtract here, I'll have 0. And then I'll have minus x there. So I can actually rewrite this as y equals, I've got x here, okay, oops, just write this better, so I have x minus x divided by 1 plus x squared, and if I take the limit, as x tends to infinity, this is going to go to 0, so I have my slanting asymptote as y equals x. Very important here. The limit as x tends to infinity is going to make this term to be 0. And this is nearly not going to be affected because as x increases, this line y equals to x just increases in that respect. Alright. So there we have the asymptotes. It's a slanting asymptote, y equals to x. That's a line through the origin. Let's go ahead and work on the turning points. I'll just get a new page here. So I'll remind you what our function looks like. Y equals x cubed divide by 1 plus x squared. So I will use the dy dx notation to find the turning points. This is actually a quotient function, so I will use a rational function, so I'll use the quotient rule. I'll assume familiar with quotient rule, so I have 1 plus x squared, then the derivative of this is 3x squared minus, I'll keep x cubed constant, then the derivative here is 2x divide by 1 plus x squared, a little square on top here. If I simplify this here, I'll actually have 3x squared plus 3x to the power 4 minus 2x to the power 4. All this divide by 1 plus x squared. So I actually have 3x squared minus x to the power 4 divide by 1 plus x squared, and this is our gradient of the curve at any point. But we know this important property that at the turning points, the gradient is actually 0. So dy dx is 0. So let's substitute 0 here. We'll have 3x squared minus x to the power 4 divided by 1 plus x squared. All this equals to 0. We just have this equals to 0, so I have the numerator here. Let me factorize out x squared, then I have 3 minus x squared, okay, equals to 0. So I'll get the values of x here as 0. Then also x is plus and minus root 3. So for every value of x, I've got to find the corresponding value of y by substituting back into the function. So for x equals to 0, y is going to be 0. So 0, 0 is a turning point. And then for x equals root 3, so I put root 3 here. You could do that using a calculator. You'll find the value of y to be approximately 1.3. Likewise, for x equals negative root 3, you'll find the value of y to be negative 1.3. So I have here positive root 3, 1.3, that's a point. And I have here negative root 3, negative 1.3. Okay, so I now have the 3 turning points for this curve, but I don't know if these turning points are maxima, minima, or points of inflection. So I'll investigate that on the next page. So let's get the nature of the turning points. Did I get this right? Okay. The nature of the turning points. Now the turning points are, of course, let's begin with 0, 0. So I'm going to have a simple table here. Okay, just before I do that, my expression for dy dx, let me write that in another color. So I have dy dx. My expression for dy dx is 3x to power 2 minus x to power 4 divided by 1 plus x squared. So I'm going to get values that are less than 0, greater than 0. I substitute them here to see what I get as the nature for every turning point. So I have here x less than 0. I want to know what happens on the left side of this. I know at x equals to 0, that's a flat point, it's a stationary point. But I want to know what happens on the right side of that point. So I'm going to substitute the value, any value of x that is less than 0. So here I want to find the sign of dy dx. Let's get any value less than 0, say negative 1. and we put it here. As you notice from all these squares to power 4, these are all even powers, so I'll have a positive sign here, which implies that the gradient is increasing. Here, this is a turning point, so I'll have this as a stationary point. Any value that is greater than 0, a positive value, will still make dy dx positive. So it means at this point 0, 0, my curve will basically look like this. It's neither maximum nor minimum. It's a point of inflection, right? Just make this better so it looks kind of like that. Let's investigate another turning point. So let's do √3 and 1.3. So of course this is the x value. That's what is most important for us here. So I have x less than √3, have x equals to √3, then I have x greater than √3. I want to investigate what happens on either sides of this point. Of course, at x equals √3, that's a stationary point there. So just like this. Okay, let's get any value that is less than √3 and substitute it here. That's always going to be positive since all these are even powers. So it's increasing. Alright, if I get any value greater than √3 and substitute it here, that's also going to be positive. So it's also increasing. So I also expect a point of inflection at that point that looks like this. And finally, let's investigate the third point, and that's negative √3 and negative 1.3. And in there we are almost done. So I have x less than, let's do this, x less than negative √3, x equals negative √3, okay, and x greater than negative √3. There we go. Should say this is dy dx. This is dy dx. Alright. So this is not there. Okay. So at x equals negative √3, that's a turning point. X less than negative √3, any value that I put here, whether negative or positive, it's always going to be positive. So that's increasing. This is a stationary point. Likewise, this is also going to be a positive if I put any value greater than negative √3 into the equation for dy dx. So I also expect a point of inflection at this point. Okay, so I'll take you back to the first page where we listed all the conditions. So we have the intercepts, we have the asymptotes, we have the turning points. We could investigate the nature of the curve, although I don't really feel that's so necessary for this curve, but I'll do it anyway because, so if I want to find the nature of the curve, first of all, I need to find the critical points. So the critical points, in this case, the critical points, of course, I take the intercepts and turning points, all values that I think might be critical to this curve, but I only take 0, 0 for this case. So let's have our expression y equals x cubed divided by 1 plus x squared. We want to test what happens when x is negative and what happens when x is positive. So if I put in a value of x that is actually negative into this expression, I'll have a negative value. If I put in a positive value, I will have a positive. So that means, I'll just show you what that means here. This is the y-axis and this is the x-axis. It means for x less than 0, on the negative side of the x-axis, we need the negative side, so we'll actually shade off the positive side. And on the other side, for x greater than 0, we want the positive side, so we will shade off the negative, just like that. So these are the two regions that we want. Okay, and now that we have everything, I think I can go ahead and sketch the curve. So let me just get a fresh page here, and I'll try to be neat now. So I have the y-axis, the x-axis. I'll just take you back. We have our asymptote y equals to x. That's a straight line through the origin. Okay, here we are. So let's do that. The asymptote. Okay, there we go. I'll also indicate the axes. So this is the y-axis, this is the x-axis. Okay, I'll indicate the turning points and the intercept. So we have 0, 0. We have root 3. Just assume root 3 is here. I'll also assume negative root 3 is somewhere here. And okay, so let's now sketch the curve. I think we have all the important information we need. So I have the intercepts. The curve must pass through here, and then there is a turning point, of course, at this very point. And then also I should mention that we don't actually need this part of the graph, so we could shade it off. So we don't need that part. Also, we don't need that part. Alright, so finally, let's now sketch the curve. So before we actually sketch the curve, the turning point here is, I'll show you that. We have negative. On the previous page, we calculated this as, okay, let me just use this. Root 3, 1.3, negative root 3, 1.3. So let's indicate that. I'll just assume 1.3, negative 1.3 is somewhere here. Okay, maybe there. Negative 1.3. I'll assume this is positive 1.3. So if you actually do this a little bit more accurate, you realize this is above the line, and this is actually somewhere below the line. Okay, so I'll now sketch the curve. Remember, this is a turning point and this is an asymptote, so the curve doesn't actually touch this line. So I'll begin by drawing a little bit like this. Okay, then oops, okay. Alright, so at this point it turns and tries to approach the asymptote as close as possible. Same thing is happening over here. Right, tries to approach the asymptote as close as possible. Okay, I'm not so accurate, but at least you get the idea of how the curve looks like. So now I'll show you how this looks like if I plot it with Wolfram alpha. So there we have the curve. This is plotted from -1 to 1. This is on a much wider scale, -6 to +6. I also plotted this using a free graphing tool called Graphmatica, and this is how it actually looks like. Alright, thanks for watching this video. If you like this, please subscribe to the channel. Also like the video, and I'll see you in my next video. Thanks.